So, welcome to this lecture number 16 of our course on fundamentals of transport processes 2. In the last lecture, we were looking at the low Reynolds number hydrodynamics, the equations and their solutions in the limit of very low Reynolds number, where we neglect the inertial terms in the conservation equation. These are also called as viscous flows or creeping flows, and the fundamental equations for these flows are basically the mass conservation equation and the momentum conservation equation, where we neglect completely the inertial terms in the conservation equation. And the stress tensor is given by minus the gradient of the pressure plus mu into grad u plus grad u transpose. Okay. It is more convenient to write it in indicial notation. It is equal to 0 and T I j . So, these are the conservation equations. These equations are quasi steady, no dependence on time in the equations themselves. So, therefore, you are not solving a partial derivative in time, where a difference in the value of some quantity, in this case the velocity, between two different time instants comes in. That means that at a given instant in time, the velocity field is completely specified by the velocities or stresses at the boundaries at that instant in time. Okay. So, for that reason it is called as quasi steady. As I said, this is a consequence of the fact that you are assuming that diffusion dominates. Therefore, the diffusion takes place over the entire domain instantaneously. Okay. The other important point is that these equations are linear. The mass conservation equation is linear in the velocity, the momentum conservation equation is linear in the velocity and the pressure, stress is linear in the velocity and pressure. Okay. And this has important consequences that we discussed in the last lecture. The flow in the limit of very low Reynolds number is reversible. That means that if I reverse the direction of either the velocity or the stress on all boundaries, then the velocity at each point in the fluid exactly reverses. If I double the velocity at or the stress on all the boundaries, the velocity and pressure at each point within the fluid increases by a factor of 2. Okay. Because of this combination of linearity and reversibility, we had discussed many interesting consequences in the previous lecture. Okay. Because of linearity and reversibility, one can also use linear superposition. That is, if I have some particular configuration where I have some objects or some surfaces moving with some velocities in some directions, I can separate that out into sub problems. In these sub problems, all the boundaries have to remain exactly the same. The velocities can be separated out into different parts and assigned to different sub problems. I solve each of those sub problems, add them up, and I get the solution for the original problem. Okay. So, that is one of the consequences of linearity and reversibility in the limit of very low Reynolds number. And I had shown you in the last lecture that many of the consequences that we are commonly used to for flows that we experience in everyday life do not apply at the micro scale for low Reynolds number flows, simply because of this difference. The equations are linear, and because the equations are linear, one is guaranteed that the solutions exist subject to appropriate boundary conditions, and that the solutions are unique. That is, you cannot have two possible solutions for the exact same set of boundary conditions that are specified. Okay. So, the consequences, the implications of this linearity and reversibility are that for a given set of equations and for a given set of boundary conditions, there exists exactly one solution, and that solution is unique. Okay. You guaranteed the existence. You cannot have a situation where no solution exists. And last class we had proceeded to try to solve these equations. Diffusion dominated regime, you would expect the equations to be in the form of Laplace equations. So, we had posed these equations in the form of Laplace equations and attempted to solve them. Okay. So, first things first, how did we do that? Okay. So, the conservation equations as I had written for the mass and momentum conservation equation. First thing I did was to take the divergence of the momentum conservation equation. Okay. So, divergence means a repeated index. And when I take divergence of the Laplacian of the velocity, which is because you can interchange the order of differentiation, the divergence of the Laplacian of the velocity is also equal to the Laplacian of the divergence of the velocity. Divergence of velocity is equal to 0, and therefore, I just get the equation for the pressure as the Laplacian of the pressure is equal to 0, or del square P is equal to 0. How do I find out the velocity field? Since I have been able to separate out the pressure and find the solution for the pressure explicitly, I can go back to the momentum conservation equation, where I consider the pressure as an inhomogeneous term. Okay. So, therefore, the original momentum conservation equation that I had, I can consider the pressure as an inhomogeneous term. So, in this equation, since I have evaluated the pressure, this can be considered as an inhomogeneous term, and so I get an inhomogeneous differential equation that is linear in the velocity. That velocity can be separated out into two parts: a general solution for the homogeneous equation without this inhomogeneous term. Okay. A general solution for the homogeneous equation without this inhomogeneous term, okay, plus a second equation in which the pressure comes in the pressure comes in, but this has only a particular solution. Any one solution that satisfies the equation. It does not have to be a general solution, does not have to contain integration constants, can be any one solution that satisfies this equation. Okay. And we saw in the last lecture that the particular solution that satisfies this is equal to 1 by 2 mu p times x I. Okay. So, the final solution for the velocity field is just u is equal to the general solution plus let me write it in indicial notation as u I general plus 1 by 2 mu p times x I. Okay. So, in this solution strategy, we have now reduced the equation to two equations, okay, for the pressure and the general form of the velocity field. This is the equation for the pressure. It says that del square p is equal to 0, where p is a scalar. Okay. This is the equation for the general solution for the velocity field, which says that del square of u general is equal to 0. U general is now a vector, okay, and the final solution for the velocity field is obtained as u is equal to u general plus 1 by 2 mu times the pressure times x I. Okay. And you can see that to solve each of these equations, you have to solve a Laplace equation. Okay. Pressure is a scalar, so you solve del square p is equal to 0 for a scalar. U general is a vector, so you solve del square u general is equal to 0, where u general is a vector. Of course, this equation contains 3 components. Okay. It is a vector equation, it contains 3 components. And this equation is telling you that del square of each component of the vector is equal to 0. That is a solution. Okay. So, if you wanted to solve it that way, you would have to solve vector scalar equations, scalar Laplacian equations for each of these, the pressure plus the 3 components of the velocity. Complicated. You now have to solve 4 Laplace equations, whereas when we did fundamentals of transport processes 1, we just had to solve one equation for either the temperature or the concentration field. Not only you have to solve these equations, you have to make sure that the solutions are now consistent with the boundary conditions as well as the mass conservation condition. Okay. Because this equation del square u general is equal to 0 does not in general satisfy the mass conservation equation. You can have solutions of this for which the mass conservation condition is not satisfied. So, for that reason, this is a complicated equation to solve the way we did it in fundamentals of transport processes 1. Okay. So, we look at ways of solving the vector equation explicitly, that is without splitting it up into individual components in this lecture. Okay. But first we go back and look at how we solved for the concentration and temperature fields in fundamentals of transport processes 1. If you recall there, in the case of diffusion dominated transport, you always had to solve del square T was equal to 0. Okay. So, you solve for example, in Cartesian coordinates, okay, if you had an x y z Cartesian coordinate system, this was the equation. And the way you solved it was by separation of variables. Okay. T is equal to some function of x. Okay. Use the separation of variable to convert this partial differential equation into 3 ordinary differential equations. The homogeneous boundary conditions reduced to an eigenvalue problem in which you had a set of discrete eigenvalues and eigenfunctions, and orthogonality relations were used for that case. Okay. Now, of course, you have 3 components of the velocity, 3 position coordinates, and trying to solve each of those will become very complicated, especially if you do not have nice boundary conditions for the velocities on the bounding surfaces. The procedure that we will use was one that we had used earlier for a point source of heat. Okay. If you recall, we had defined a point source, okay, as something that emits, okay, source strength Q, okay, which is emitting heat in all directions. Okay. In this particular case, because the heat is emitted equally in all directions, the configuration is spherically symmetric. Okay, the configuration is spherically symmetric. Okay. And because of that, you have the equation in a spherical coordinate system in 3 dimension becomes 1 by r square d by dr of r square partial t by partial r is equal to 0. Okay. So, that is the solution, that is the equation spherical coordinate system. Okay. You can solve this quite easily and get t is equal to some constant by r plus C 2. How do I get that constant out? I get it from the condition that the total heat Q is equal to integral over any surface. If I take any surface over here, integral over that surface of the total flux in the r direction. Okay. This has to be equal to integral over the surface of minus k times partial t by partial r. And this gave us the temperature field for the point source, okay, is equal to q by 4 pi k r okay, plus some constant. Okay, this constant can be any value. Okay, it's basically this is determined from the temperature far away from the object, because as you go far away, R goes to infinity, therefore, temperature has to go to some constant value. So, this constant C2 is basically the temperature far away from the object. So, basically the temperature field decreases as 1 over R as you go far away from the object itself. Okay. We had done more than this. We had actually solved the Laplace equation in a spherical coordinate system in the previous lecture in Fundamentals of Transport Processes 1. In that case, the equation becomes 1 by R square d by dr of R square dt by dr plus 1 by R square sin theta. So, this was the Laplace equation in a spherical coordinate system. R theta phi coordinate system, and we had solved this equation once again by separation of variables, by separating out t is equal to r of r f of theta times h of phi, and we had got the solution as 1 by r power n plus 1 p n m of cos theta e power I m phi. Okay. We had got two sets of solutions where p and m of cos theta were the Legendre polynomials. Okay. So, I got one series of solution in which the temperature decreased as you went far away. So, this was 1 by r power n plus 1 p n m of cos theta e power I m phi, plus the second was r power n. Okay, so, let me just write the general solution. A n m by r power n plus 1 plus b n m r power n p n m of cos theta e power I m phi. Okay. Where in general we find that m goes from minus n to plus n and n is equal to 0 to infinity. These discrete eigenvalues m and n, if you recall, we had got from the condition that the solution has to be finite at theta is equal to 0 and theta is equal to pi. Okay. So, these were the solutions that we had got by separation of variables. I had given you a physical interpretation of these solutions. Okay. So, for n is equal to 0, this just reduces to t is equal to some constant by r plus some constant. Okay. Because for n is equal to 0, m is equal to 0, p and m is equal to 1 and e power I m phi is also equal to 1. Okay. For n is equal to 1, okay, m can go from 0, minus 1 and plus 1. Okay. So, m is going from minus n to plus n. So, m varies between minus 1, 0 and plus 1. Okay. So, for n is equal to 1, for m is equal to 0, we got the solution as t as some constant a 1 0 by r square cos theta plus b 1 0 r cos theta. Okay. And if you recall, I had given you the physical interpretation of this. Okay. The physical interpretation of this first term. the physical interpretation of this first term, if you recall, corresponded to the combination of a source of heat and a sink of heat plus Q minus Q located at some small distance L above and below, okay. A source and a sink giving you a dipole, okay, located at distance plus L and minus L above and below the z axis, strength plus Q and minus Q in such a way that there was no net source, because there is a source plus Q and a sink minus Q. The net heat coming out into the domain is 0. Okay. In the limit as L goes to 0, L goes to 0 and QL being finite, you get a source dipole. Okay. The source dipole is something that looks like this. Okay. If it is separated along the plus and minus z axis, a small distance from the origin, in such a way that the distance goes to 0, but the source strength or the sink strength times that distance remains finite, you get this second term. There is no net source. So, therefore, the contribution proportional to 1 over r is equal to 0, but you get a net source and a sink, and that gives you this term, okay, this dipole moment, okay, the source and sink of heat separated by a small distance. Similarly, for n is equal to 1 and m is equal to plus 1, okay, we saw that it corresponded to 2 source and sink separated along the x axis, and for m is equal to minus 1, it corresponded to along the y axis. Okay. And each of these solutions satisfies the orthogonality condition. So, I can use the orthogonality condition to get back the solutions for the spherical harmonic expansion. Okay. So, that is how we had done it in a spherical coordinate system. Okay. Similarly, for n is equal to 2, m is equal to minus 2, minus 1, 0, plus 1, plus 2. There are 5 solutions for n is equal to 2, minus 2, minus 1, 0, plus 1 and plus 2. And I had showed you that each of these corresponds to one particular arrangement of sources and sinks. Okay. So, if you have this as the x1, x2 and x3 axis, okay, you have arrangements in which you have 2 sources and 2 sinks along the x1 and x2 axis. Then you have 2 sources and 2 sinks along the x and z, okay, plus. Then you have one along the and then these corresponds to the x y, y z, x z. Then you have one that is basically called x square minus y square, in which you have a source and sink that is arranged along the x y plane, okay, but not along the axis. Okay. Okay. And then finally, you have 2 sources and sinks arranged along the z axis. Okay, these were the 5 solutions that we got, combinations of sources and sinks. Okay. So, these were physical interpretations of the results that we got by solving the Laplace equation in spherical coordinates by separation of variables procedure. Okay. In case you are not familiar with this, kindly go back to Fundamentals of Transport Processes 1 and revise what we had done in that particular solution of the Laplace equation. Okay. Here we will use the exact same solutions, except we will give them a different physical interpretation. Okay. We will use the exact same solutions, except we will give them a different physical interpretation. Okay. So, basically we want to solve the Laplace equation in spherical coordinates for del square of something is equal to 0. Okay. I know one solution for this. This thing can be a scalar, it can be a vector, it can be a tensor, okay, it can be anything. Okay. I know one particular solution for this. If this is a scalar, then I know that I have a solution phi is equal to some constant divided by r, okay, plus another constant. Okay, but we will just define this correct to one unknown constant, okay, in the field. So, this solution I have. Okay. Let us call this the fundamental solution. Okay. I will put it with a 0 over here. This is the fundamental solution. So, if this is the equation, the Laplacian of phi naught is equal to 0, then if I take the gradient of this solution, that is also equal to 0. Okay. In other words, if I take gradient of del square phi naught, this is also equal to 0, because if I take the gradient of any function, if that function is equal to 0, its gradient is also equal to 0. I can rewrite this, interchange the order of differentiation, okay, that is always possible. So, I will rewrite this as del square of grad phi naught is equal to 0, okay, interchanging the order of differentiation. That means that this term in the brackets here is also a solution of Laplace equation. Okay. Del square of phi 1 vector, this is also a solution of Laplace equation. Okay. In indicial notation, I write this as del square of phi 1 I is equal to 0. Okay. So, that means that this is also a vector solution of Laplace equation. Okay. It is a vector solution. Of Laplace equation. Okay. How do I get this vector solution? I have to take the gradient of the fundamental solution. Okay. So, let us see how we do that. The easiest way to take the gradient is to take it in Cartesian coordinates. Easiest way to take the gradient is in Cartesian coordinates. Okay. This coordinate system, this is r, okay, and we know that in a Cartesian coordinate system, r is equal to square root of x 1 square plus x 2 square plus okay, and phi naught is equal to c by r is equal to c by root of x 1 square plus x 2 square plus x 3 square. And how do I take the gradient? Okay. Gradient of phi naught is equal to E 1 d by dx 1 of 1 over r. Okay. It is a constant. So, okay, times the gradient of the fundamental solution. Now, this is pretty easy to do, because I have c constant by r, which is 1 by square root of x 1 square plus x 2 square plus x 3 square. Okay. For future use, we will just define the definition of the gradient itself. Okay. The definition of the gradient of r is equal to E 1 d by dx 1 plus E 2 of square root of x 1 square plus, okay. This becomes E 1 x 1 by root of plus So, I can write this as, since square root of x 1 square plus x 2 square plus x 3 square is just r, I can write this as summation of E I x I by r. Okay. In our indicial notation, we of course do not write down the summation and the unit vector. So, this just is equal to x I by r. Okay. So, this is equal to partial r by partial x I, the gradient of r. Is equal to x I by r. Okay. Therefore, the gradient of phi naught, I will write it in indicial notation, the gradient of the fundamental solution is equal to of some constant by r. Okay. This is equal to minus c by r square partial r by partial x I, okay, using chain rule for differentiation. Differentiate with respect to r first and then differentiate r with respect to x I. Okay. And since the derivative partial r by partial x I is equal to x I by r, this gives me minus c x I by r cubed. So, this is a vector solution of the Laplace equation. Okay. Phi 1 I is equal to minus c x I by r cubed. So, this vector solution contains in it 3 components. Okay. This vector solution contains in it 3 components, x 1 by r cubed, x 2 by r cubed, x 3 by r cubed. But rather than considering it, rather than considering 3 different components separately, I have just assembled them into a vector. Okay. So, this is a vector solution of the equation. If phi 1 I satisfies the Laplace equation, then its gradient also satisfies the Laplace equation. Okay. So, that is if del square phi 1 I is equal to 0. If I take the gradient of the whole thing, I am taking the gradient, no repeated index. Okay. So, that means that partial by partial x j of phi 1 I is equal to 0. I am sorry. Interchanging the order of differentiation once again, del square of partial by partial x j of phi 1 I is equal to 0, which means that del square of phi 2 I j is equal to 0, where phi 2 I j is now a tensor solution of the Laplace equation. Okay. It is a second order tensor. Okay. Get it by taking the gradient of the first order tensor. Okay. I will define it to only within a multiplicative constant, phi 2 I j is equal to partial by partial x j of minus c x I by r cubed. I have to do the differentiation of this using the chain rule, because I have x I in the numerator and r cubed in the denominator. Okay. So, this will give me minus c times partial by partial c by r cubed partial x I by partial x j minus c x I partial by partial x j of 1 over r cubed. Partial x I by partial x j is just delta I j. So, I get minus c delta I j by r cubed plus 1 over the derivative of 1 over r cubed with respect to x j. What I need to do is use chain rule for differentiation. I will get minus c x I into minus 3 by r power 4 into partial r by partial x j. So, this will be minus c delta I j by r cubed, okay, and partial r by partial x j is equal to x j by r. So, I will get plus 3 c x I x j by r power 5 is equal to c into minus delta I j by r cubed plus 3 x I x j by r power 5. So, that is the second tensor solution, second order tensor, okay, for the Laplace equation. It automatically contains 9 components, okay, and in Cartesian coordinate system each of these would individually satisfy the Laplace equation. I could do this once more and get a next higher order tensor. Okay. I will not go into the details of how the calculation is done, but the next tensor is equal to delta by delta x j of phi 2. I am sorry, I should take x k. And if you do the same procedure, expand out by chain rule, and you will get c into minus 3 delta I j x k by r power 5 minus 3 delta I k x j by r power 5 okay, plus 15 x I x j x k by r power 7. Okay, so, that is the next higher solution. This is a third order tensor, 27 components, 3 power 3 and so on. You can get the next higher and the next higher and so on. Okay. What do these physically mean? Okay. So, let us go to the physical interpretation of the spherical harmonic. Okay. Phi naught. I will not put in the constant for now, because these can be multiplied by any constant and they will still satisfy the Laplace equation. Okay. So, I showed you that this was equal to a point source. Okay. 1 by r, it was spherically symmetric point source. Okay. This, if you recall, was the same as the solution for the source. The equation that I had for the temperature field is equal to sigma A n m by r power n plus 1 p n m of cos theta e power I m phi. Okay. This was the solution for n is equal to 0 and m is equal to 0. Okay. The next one was minus x I by r cubed. That had 3 solutions, that is x 1 by r cubed, x 2 by r cubed and x 3 by r cubed. Okay. So, if you expand out these solutions in a Cartesian coordinate system, there are 3 minus x 1 by r cubed, E 1 minus x 2 by r cubed, E 2 in the spherical coordinate system. Okay. If you recall the spherical coordinate system that we had, this was the distance r, okay. This is theta, this is the angle phi, okay. And you know that x 3 along the 3 axis, x 3 is equal to r cos theta, x 1 is equal to r sin theta cos phi, and x 2 was equal to r sin theta sin phi. Okay. This is the expansion of the coordinates x 1 and x 2, x 3 in the spherical coordinate system. X 3 is r cos theta, because the angle between the x 3 axis and the radius vector is equal to theta. The projection is equal to phi, therefore, x 1 is equal to r sin theta cos phi, and x 2 is equal to r sin theta sin phi. So, using this we get these three solutions, okay, for this vector minus r sin theta cos phi by r cubed E 1 minus r sin theta sin phi by r cubed E 2 minus r cos theta by r cubed E 3. Okay. If you recall, these are the exact same solutions that we got for a source and a sink separated by a small distance in the spherical coordinate system. Okay. So, this in the x 3 direction, okay, the solution was n is for n is equal to 1, m is equal to 0, okay, some constant a 1 0 a 1 0 by r square cos theta, okay, for separation along the x 3 direction or the z direction. Okay. You can see that this one is identical to the vector solution component along the 3 direction for this gradient of the fundamental solution. Okay. For n is equal to 1, m is equal to 0, okay, you get one solution. If you recall, when n is equal to 1, m is equal to minus 1, 0 and plus 1. Therefore, there are 3 solutions. The solution for n m is equal to 0 corresponds to the exact same solution in the gradient of the potential of the fundamental solution along the x 3 direction. Okay. Then I had 2 solutions for along the x 1 direction, n is equal to 1, m is equal to 1. I had a solution which was a 1 1 by r square sin theta cos phi. This one is identical to the solution here. Okay. Note that the negative sign does not really have any physical significance, because if phi 1 is a solution, its negative is also a solution. Okay. So, this corresponds to n is equal to 1, m is equal to 1, and this one, it is easy to see, corresponds to n is equal to 1 and m is equal to minus 1. Okay. This is 2 sources and sinks separated along the x 2 direction. So, this is plus minus sin theta sin phi. Okay. So, the components of this vector solution are the exact same solution you get for the dipoles with the dipole moment along the 3 coordinate axis. Okay. In that case, when we solved in terms of Legendre polynomials, we got 3 solutions. For n is equal to 1, there were solutions for m is equal to minus 1, 0 and plus 1. Those 3 solutions are exactly the components of this vector solution that I get when I take the gradient of the fundamental solution. I get a vector with 3 components. Those components exactly correspond to the solutions that I get here. Okay. The same thing can be shown for the next higher order term in the expansion. Okay. Phi 2 I j is equal to minus delta I j by r cubed plus 3 x I x j by r power phi. Okay. This is a second order tensor, okay, a second order tensor, and therefore, it has a total of 9 components. Okay. However, it is also symmetric. If I interchange I and j, I should get exactly the same result, because if you recall, I took this by taking gradient of the fundamental solution 2 times. Okay. So, phi 2 I j is equal to partial by partial x j of partial by partial x I of phi naught. I took gradient 2 times. That is equal to, I can easily interchange the order of differentiation because x I and x j are independent variables. So, this is also equal to partial by partial x I of partial by partial x j of phi naught. This is equal to phi 2 j I. Okay, so, it is a symmetric tensor and therefore, it has 6 independent components. Also, because it is a symmetric tensor and it is obtained by taking the 2 gradients of the fundamental solution, it is also traceless. Okay. Traceless means that the sum of the diagonal terms is equal to 0. How do I get the trace of this tensor? I can get the trace of this tensor by multiplying it by delta I j. Okay. So, delta I j times phi 2 I j is equal to delta I am sorry. Okay, when you multiply delta I j by this solution, it is non-zero only when I is equal to j. So, I could replace j by I in phi 2, okay, and I will get a scalar phi 2 I, only one repeated index. Okay. On the left hand side you have 2 repeated indices. So, it is a scalar. Okay. So, this is equal to delta I j into minus delta I j by r cube plus 3 x I x j by r power phi. Delta I j into delta I j is delta I I. Okay. So, this is equal to minus delta I by r cubed plus 3 x I square by r power phi. What is delta I equal to? It is equal to summation I is equal to 1 to 3 of delta I. There is one summation, no unit vector because it is a repeated index. So, delta 1 plus delta 2 plus delta 3 is equal to 3. Okay. So, it is equal to minus 3 by r cubed plus x I square is x 1 square plus x 2 square plus x 3 square, that is also equal to r square, because x 1 square plus x 2 square plus x 3 square is equal to r square. So, this becomes equal to plus 3 by r cube. So, I can cancel out that r square by r power 5 is equal to 1 over r cube. So, this is equal to 0. So, the trace of this second order tensor is identically equal to 0. Okay. Not a surprise, because if I take the trace of the second order tensor, you will recall that delta I j times phi 2 I j is equal to, if I write this as 2 gradients acting on the fundamental solution. Okay. In this I can replace I by j. Okay. I am sorry, I can replace j by I, because delta I j is non-zero only when j is equal to I. And I will get partial by partial x I of partial by partial x I of phi naught, which is the Laplacian of phi naught, which has to be equal to 0. Okay. The Laplacian of phi naught has to be equal to 0. Okay. So, therefore, what I have shown you is that the second order tensor solution phi 2 I j, it is a second order tensor, it is symmetric because interchange of indices makes no difference. It is also traceless. Symmetric matrix has 6 independent components, out of which if it is traceless, the sum of the diagonals have to be equal to 0. Okay, the sum of the diagonal elements have to be equal to 0. So, therefore, in this 3 by 3 matrix, okay, phi 2 1 1, maybe not write it down. Okay, this is the second order tensor. symmetric 6 independent components. It is also traceless, that means the sum of the 3 diagonals has to be equal to 0. So, there is total of 5 independent components in this second order symmetric traceless matrix. Okay. And if you recall, the solution A n m, okay, by r power n plus 1 p n m of cos theta e power I m phi, okay, for our spherical harmonic expansion. For n is equal to 2, this has A 2 m by r cubed p e power I m phi. Okay. It goes as 1 over r cubed. Okay. You can see that each of these actually goes as 1 over r cubed. Each of these goes as 1 over r cubed. The first term is delta I j by r cubed. Second term is 3 x I x j by r power 5. Both x I and x j are r cos theta, r sin theta cos phi, r sin theta sin phi. Therefore, when I divide by the 2, I will get some function of angle divided by r cubed. Okay. Exactly the same dependence on r that I have over here. Exactly the same dependence on r that I have over here. In this, at n is equal to 2, m is equal to minus 1, I am sorry, m goes from minus n to plus n. So, it is equal to minus 2, minus 1, 0, plus 1 and plus 2, 5 components. Exactly the same as the number of independent components in this second order traceless tensor. So, there are 5 components here. In fact, you can show that each one of these components in the second order tensor is a linear combination of the 5 components in this spherical harmonic solution. So, therefore, there is a 1-to-1 correspondence between the solutions scalar, vector, tensor that I get here with the spherical harmonic solutions that I get there. Okay. For n is equal to 0, it is spherically symmetric or source. N is equal to 1, 3 components corresponds to the vector solution that I got by the gradient of the fundamental solution. N is equal to 2, tensor solution has 5 independent components because the tensor is traceless, corresponds to the 5 components that I get, 5 solutions that I get for n is equal to 2 and m is equal to minus 1, minus 2, minus 1, 0, plus 1 and plus 2. So, the scalar solution, the fundamental solution decreases as 1 over r as r becomes large. The vector solution decreases 1 over r square x I by r cubed. The tensor solution decreases as 1 over r cubed corresponds to n is equal to 2 and so on. So, these are the scalar, vector and tensor solutions that you get. If you recall, when we did the solution for the temperature field, we not only had that, but we also had a second set of solutions. We had a second set of solutions. Okay. Therefore, the solutions that we got from the point source are not the only ones. Okay. I got the solutions from the point source as phi naught is equal to 1 over r, okay. 1 over r power n plus 1 with n is equal to 0. Okay. For that same value of n, there is another one which goes as r power plus n. Okay. There is another solution which goes as r power plus n, and for n is equal to 0, this is just a constant. Okay. This is just a constant r power plus n. For n is equal to 0, I get the solution, this solution for this one by multiplying the first solution by r power 2 n plus 1. Okay. I multiply this by r power 2 n plus 1 to get the other solution. If you recall, these are the decaying harmonics, they decrease as r goes to infinity. These are what are called the growing harmonics, that is, they increase as r goes to infinity. So, corresponding to the source solution 1 over r, there is also a growing harmonic solution which is just a constant, which is not too surprising. If you recall, when we solved for the temperature field, we just got q by 4 pi r plus T infinity, and this is the constant solution. For the vector solution, one that I got was xi by r cubed, okay, n is equal to 1. Okay. This goes as 1 over r square. The other solution should go as r power plus 1, okay, r power 1 over r power n plus 1. So, n is equal to 1 means you get 1 over r square xi by r cubed. The other one should go as 1 over r power plus 1. You get that by multiplying the first solution by r power 2n plus 1. In this case, since r power 2n plus 1 is equal to r cubed, the other solution is just xi. The next higher is equal to minus delta I j by r cubed plus 3 xi xj by r power 5. This is for n is equal to 2, it goes as 1 over r cubed. The growing solution I multiply by r power 2n plus 1, 2n plus 1 is r power 5. Okay. So, I have to multiply by r power 5 to get the growing solution, and that growing solution will be equal to minus r square delta I j plus 3 xi xj. Okay. So, we got the decaying solution by taking successive gradients, okay, of the solution for the point source. Point source went as 1 over r. We took successive gradients of that solution for the point source to get all the decaying harmonics. There is another set of solutions for the Laplace equations in which the solutions increase as r goes to infinity. Those are the growing harmonics, and in this case you get this by multiplying the decaying harmonics by r power 2n plus 1. And in that way we can get solutions which are scalars, vectors and tensors for the Laplace equation. These are exactly the same as what we got using spherical harmonics expansions, as well as by looking at point sources, dipoles, quadrupoles and so on. But since these are in the form of vectors, they will be more convenient for us to express velocity fields in terms of these. So, in the next lecture we will use these spherical harmonics expansions for solving the simplest problem that we can, that is for the settling of a sphere under gravity in a viscous fluid. We want to solve the Navier-Stokes equations in order to find out the velocity field around the sphere, and ultimately to find out what is the drag force on the sphere. If you recall, the drag force on the sphere is given by the Stokes law. The force is equal to 6 pi mu r times u, where r is the radius of the sphere and u is the velocity. So, next lecture we will look at how we can get that solution, and as well the velocity and the pressure field at each point in the fluid. So, we are going to solve for the velocity and the pressure field subject to the boundary condition on the surface of the sphere using these spherical harmonic expansions in order to find out what is the velocity field due to a sphere settling at constant velocity in a fluid, and also to find out what is the drag force. So, if you are not familiar with the spherical harmonics expansions, please go through this once more. I will revise it a little when I start in the next lecture, and then I will proceed to actually calculate the velocity field using spherical harmonics expansions, as well as using the linearity of the Stokes flow at low Reynolds number. We will see you then. Thank you.